Well, our study is concerned with 21,000 years ago, which is the last glacial maximum. And there's evidence of very dynamic changes before that and between that time and the present. So as the large ice sheet that was up in Canada and the northern part of the US melted away, climate started changing towards what we see today. And there's even evidence that climate was, warmer and drier than pre-industrial climate at some time between the last glacial maximum and today, so about 6,000 years or so ago. So there's been lots of changes between now and then, but predominantly we've been moving from a wetter, colder climate into the warmer, drier climate that we have today out west. We can't easily look back in the past and say there were 400 millimeters of precipitation a year, but we can say, this period was wetter than the present. And we use a number of different things. So one method is by looking at those lakes, by seeing the remnant shorelines, which often are associated with different geomorphic features like beaches or the precipitation of some minerals like bathtub rings around the shores of these lakes. And we can date those minerals and say, okay, the water level was here, 18,000 years ago or something like that. You can also take a sediment core through those lakes and look at the sediments that were deposited, and that gives you a record of lake water chemistry, which might change based on the amount of water that's coming and going. You can look at fossil pollen, which tells you something about the vegetation that was around the lake. And based on what we know of where those kinds of plants like to live today, we can make inferences about what the climate was like in the past. And then the research that I do myself is looking at cave deposits or speleothems, and those grow from groundwater, from water that starts as rain and trickles through the soil and trickles through rock and precipitates a stalagmite mainly. That's what we're looking at. And the chemistry of that water that's captured in that cave deposit tells you something about maybe temperature or rainfall or infiltration above the cave. So we took all of those things together and in this study and used it to get kind of a regional picture of what climate was like at this one snapshot in time, 21,000 years ago. There were several things that I just loved about this study. I mean, one of them was, people have been looking at paleoclimate record, or at paleoclimate in the West for 100 years, right? There's paintings of these fossil shorelines around the Great Salt Lake, and there's papers going back, a very long time that where people were thinking about these problems. And so in putting this study together, I got to go back and really read all of that old literature, which I had kind of read in the past, but it was great to sort of see where we have been and where we're going. And putting all of those things together spatially like that was really interesting because it sort of solidified patterns that people have been thinking about for a long time. I mean, the idea of the storm track shifting southward is not, a new idea. It's something people have been thinking about for a while. But what we saw when we did this was really the shape of what that looked like. Like we see wetter conditions in the southwest, drier conditions in the north, and then we see this transition that has what we think is an interesting shape. It sort of slopes from the California-Oregon border on the coast down through the northern Great Basin into the Rocky Mountains. And the shape of that was new to us, and it also reminded me a lot of the kind of precipitation patterns we see today in response to different El Nino cycles. So, the southwest and the northwest will respond very differently, but then the presence of that ice sheet really drives a different shape to that pattern from what we see today. What our study provides is kind of a way to benchmark those models. We have evidence from the ground that says climate was like this at this time, and we can compare to those models and say, okay, this model, gets the right answer. If we assume that the paleoclimate record is the right answer, but this model matches with what we see in the paleoclimate record, and this model doesn't, and so that can give you an idea of, where models might need to be fine-tuned or which ones are doing things correctly from the paleo perspective, and then that can give you information to help fine-tune those future scenarios so we can understand, where we might be going in terms of precipitation in the future.